we use angular variables in rotational kinematics equations. When we talked about linear motion in 1 and 2 dimensions, we learned about variables that describe the motion of an object: displacement, velocity, and acceleration. In rotational motion, an object is rotating or turning around a fixed axis. This type of motion requires new but similar variables: angular displacement, angular velocity, and angular acceleration. The axis of rotation of a rotating body, in this case coming out of the screen, is the center of the rotational path. A radial line is a line that intersects the axis of rotation perpendicularly. As an object turns about its axis of rotation, a radial line will sweep out a given angle, delta theta. This angle, delta theta, is called the angular displacement of the object. Angular displacement can be considered to be a vector quantity since direction matters. We don't typically draw it with vector arrows, however, and we let positive and negative signs denote direction. The angular displacement is considered to be positive if motion is in the counterclockwise direction, and negative if it's in the clockwise direction. If we choose a point on the body, then as the body rotates, the point will trace out an arc of length s. We call s the arc length. This arc length is measured at a radius r from the center of the circle. The angle theta is associated with this specific arc length and radius. If the arc length and the radius are given in the same units, we can divide s by r to get a value for theta in units of radians. Radians might be a new idea. We're more familiar with degrees when we're talking about angles, so let's relate radians to degrees. We know that a circle has 360 degrees, but how many radians are in a circle? Theta in radians is given by the arc length divided by the radius, so we'll draw the radius and the arc length of this circle. We can see that the arc length of an entire circle is equal to the circumference of the circle, which is equal to 2 pi times the radius of the circle. So if we substitute that in for our theta expression, we get 2 pi r over r, which gives us 2 pi radians in a circle. So that means that 2 pi radians equals 360 degrees, and 1 radian is equal to 360 degrees divided by 2 pi, which comes to 57.3 degrees. Earlier, we found average linear velocity by dividing the displacement by a time interval. Similarly, average angular velocity is found by dividing the angular displacement by a time interval. Angular velocity is written as the Greek letter omega. Angular displacement is given in radians, so angular velocity is in units of radians per second. And just as with linear velocity, instantaneous angular velocity is the angular velocity of an object at any given instant, delta theta over delta t as t approaches 0. Angular velocity is considered a vector quantity since direction matters, even though we don't generally use vector arrows when writing it. Just as with angular displacement, counterclockwise is considered to be the positive direction, and clockwise is the negative direction. The magnitude of the angular velocity of an object is sometimes called the angular speed. We also previously found average linear acceleration by dividing linear velocity by a time interval. Similarly, average angular acceleration is found by dividing the angular velocity by the time interval. Angular acceleration is written as the Greek letter alpha. Angular velocity is in units of radians per second, so angular acceleration is in units of radians per second squared. And just as with linear acceleration, instantaneous angular acceleration is the angular acceleration of an object at any given instant. Angular acceleration is also a vector quantity, with the positive direction being counterclockwise and the negative direction clockwise.